So, this whole talk is basically trying to convince you that the title is not false, it's true. Okay. So a little advice can indeed be very helpful. This is joint work with Jeff Edmonds, Faith Ellen, Faith is here, and Tony and Pitasi. So first a disclaimer, as I was just telling Faith, this talk is going to be about a communication problem that's motivated by data structures, and I'm not an expert in data structures, so if there's a question about data structures, I'll deflect it conveniently to my co-author. Okay. All right, so let's get started. So here's the dynamic problem that we are interested in. So imagine you have a graph on n vertices, and this graph is sort of being dynamically, incrementally given to you. Okay, so it's not given at one go. It comes in incrementally. So for instance, there might be a request, connect the vertex number 1 with vertex number 7 by an edge. Okay, and the idea is you're maintaining a data structure that sort of takes in this request as they come in and incrementally builds this data structure. So then you might get a next request. Well, now the edge connecting vertex number 2 to vertex number 8 needs to be put in. And you update your data structure. You do this as the requests come in. And then there might be a request that's a little different type, which says, well, in the current graph that you have, what's the length of the shortest path connecting vertex 1 to vertex 10? Okay? And in this particular case, the answer is 2. The thing in red that I've shown here turns out to be the shortest path. Okay, so the data structure algorithm should be able to quickly, by reading as few bits as possible, be able to answer such queries. Okay. And now there might be requests like, well, maybe this is a network, a link which was so far functioning well, connecting vertex 3 to vertex 10 just went down. So you don't have that edge anymore. And again, you should be able to take that request incrementally, update your data structure so that you're ready to answer the next query, which is, again, the same query, what's the length of the shortest path connecting vertex 1 to vertex 10? And of course, the answer now has changed. It's 3. And again, the path now is very different, the shortest path. But the idea is, since this request sort of again came incrementally, you should be able to give a quick answer. Okay? So this goes on for a while. Each time, the graph has to be updated, and you want to be able to quickly give the answer by querying as few bits as possible in your data structure. Okay? So as I said, the goal is to create a data structure that supports this add, delete, and query operations. And on per operation, amortized over each operation, it spends as little a time as possible. Okay? And what seems to be the gold standard is, can you suppose this graph was over n vertices, can you spend amortized polylog of n time in servicing this request, amortized? Is that possible? So if that were possible, we would say that yes, there is an efficient dynamic data structure for solving this problem. Okay, and this seems like a very hard problem. It seems, I'm going to convince you about try to convince you about the hardness of the problem by the next slide. So no such data structure algorithm is known, and this is the problem called the dynamic shortest path problem. It's the shortest path problem, but the dynamic version of it. Okay. So here's what appears to be a very simple graph, which already seems like hard to work with. So here's the graph. The graph has, these are the three sort of partitions of vertices. So I have three groups of vertices: the x vertices, the v vertices, and then there's a singleton vertex called denoted by y. And requests will come in phases. So there are 3 phases. Okay, in the first phase, you get requests connecting the leftmost partition to this middle partition. Okay, so for instance, the request might be add x1 to v2 or add x1 and add x1 to v3. So the requests are of this type. First, you set up the set of vertices that you want to connect in v to x1. Okay. Then you get for x2 and so on, and you build up the graph for every guy, including xk. Okay. So I'm showing you a sequence of fixed requests, okay, and which seems already hard, as you will see. Okay, and then in the second phase, so that's the once you connect up x with v, phase 1 ends. In phase 2, now you want to connect vertex y to a subset of the vertices of the v vertices. Okay, so that's phase 2. And now in phase 3, you're asked, well, what's the length of the shortest path connecting, let's say, vertex xi for some I to y? Okay, and if you think about it, well, this answer is 2 precisely when the neighborhood of xi. So xi, say xi is here, it's connected to some subset of vertices v, right? And if that neighborhood and the neighborhood of y intersect, then the length of the path is 2. Otherwise, the length of the path is at least 4. Maybe they don't. Maybe there is no path, but it certainly cannot be 2 or less. Okay, that happens exactly if this neighborhood set of x intersects with the neighborhood set of y. Okay, so let's look at the time budget. So there were kn requests that came in to build up the graph on the left-hand side. And if I'm aiming for an amortized time of tau, then I get order kn tau time for phase 1. Okay? In phase 2, I have n requests potentially, right? I mean, specifying what needs to be connected to y. And so I get at most order n tau time. Okay? And then in phase 3, again, if I'm shooting for amortized time tau, I should be able to give out the answer in just order tau time. Okay? And now let's say that k is very large. I mean, much larger than n to the 1 plus gamma. Okay? Then with this setting of parameters, if tau is polylog of n, okay, in phase 1, you basically didn't have, intuitively, you didn't even have time to check all the neighborhoods. Okay? So because you got time k times n times tau, and tau is just polylog. Okay? Oh, sorry. Let me back up. Sorry. I meant to talk about phase 2. In phase 2, if tau is polylog, you didn't even have enough time to check all the k different sets corresponding to the neighborhood of vertex xi for each I. Right? So if tau is polylog, then you didn't get enough time. Yet in polylog of time, which is much, so tau being polylog of n means it's much smaller than n, you have to be able to answer whether one of the, the ith set intersects with the y set. Yeah, you don't even get n time. Right? So this seems very hard. Okay, any questions at this point in time? Yes. Yes. Yeah, so here actually I can make this sort of n very large so that you get order n tau time essentially for just this phase 2. So this seems hard, but how do we formalize this notion? So what I'm going to say is there is some sort of information theoretic bottleneck, and this comes out in a communication game played between some players. So to capture this communication bottleneck, what I will be doing is I'll talk about a slightly different model, not quite the standard two-party model of Alice and Bob. There will be a third player who will give advice. Okay, so let's just jump into the model. So you're all now familiar with two-party model. So here it's an advice model, so it's sort of a very intriguing model. So here's the thing. Now Alice, there are two players as before, Alice and Bob. Things are written on their forehead, unfortunately. So Alice on her forehead has got x1 through xk, and Bob has got y. Each of these xi and y, think of them as n-bit strings. Okay, and there is some function f, small f, okay, which is a bipartite function, which depends on two n-bit variables. Okay, and so this function is such that it's sort of hard for just between Alice and Bob. So if Alice was just given one of these x's and Bob had this y, and they were asked to compute this small f, okay, let's assume that this was a very hard task for Alice and Bob by themselves to do that. Okay, so it had very large communication complexity. Okay, but now Alice has got k instances and Bob has got just one instance, so this is the asymmetry. So of course, what they want to do is they want to solve this f of x I y. So they both know I, but as I assume by themselves they can't solve it. This is hard. So here's where a third player in the form of Charlie comes in. Okay, and what's Charlie's role? Charlie has got I on his forehead, so he can't see. I forgot to mention, so by forehead, the reason I'm talking about forehead is because you should think that nobody can see their own forehead, but they can see the foreheads of everybody else. Okay, so Charlie, everything is accessible to Charlie except this crucial index I, which is a number from 1 through k. Okay, and so Alice and Bob seek Charlie's help in a particular way so that they can solve the problem, because by themselves the problem is very hard. And what is the way Charlie is going to help? Well, Charlie is going to speak just once, right at the beginning of the game. Okay? And what he's going to do, he's going to give an expert advice to Alice. Why is he going to give this advice to Alice? Because if you think about it, Alice has the largest information sort of missing. Because x1 through xk, which is about k times n bits, is on Alice's forehead. This is what she does not see. Okay? So Charlie is supposed to send a private advice to Alice, and so that, given that advice, suddenly the problem becomes easy. The hard problem becomes easy. But Charlie's advice has to work for all possible i's, because Charlie doesn't know an I, the relevant I. Okay? So here's Charlie who creates an expert advice, and then Charlie bolts from the game. Okay? Hereafter, it's a two-party game. So that's why I call it an advice model. There's an advice given by an expert, and the expert leaves. And of course, so as I said, thereafter, we want to find out if Alice and Bob can suddenly reduce the total number of bits that they now need to compute this game. Of course, it depends on the length of the advice that Charlie gives. If Charlie was, if there was no budget for Charlie, Charlie could easily give k bits of advice, and then, Alice does not even need to consult Bob, because Charlie would compute all the answers. These are Boolean answers, right? So Charlie could give a k-bit string where the ith bit is the answer of f of xi y, right? So if Charlie was allowed to give k bits out, the answer would be known to Alice immediately. Okay? The point is, Charlie, as I said, this is the thing. So if Charlie is allowed to only give little o of k bits of advice, okay, so far fewer than k. Okay, so if Charlie gave no advice, then Alice and Bob were left to themselves. If Charlie gave all the advice that he could have given, then, Alice could solve the problem by herself. The point is, what happens if Charlie gives, not zero advice, not k bits of advice, but somewhere in between? Does the problem suddenly become easier? Okay? So the crucial thing which we will see is that, Charlie's advice depends on both x and y. Yes, little f is Boolean function, yeah. Right. So capital F is, by virtue of that, also a Boolean function. Yeah. So this model was introduced by Patrascu in 2010. Okay, and this is I think it's a very nice model, because you're taking a two-player game and sort of slightly perturbing it by this advice, and you want to understand, how much does the robustness of the hardness of a function, how much does it alter by allowing Charlie to give advice, okay? Now, if it seems like, it seems like, since Charlie is allowed to give only so few bits of advice, essentially Charlie will not be able to say much about some xi, and therefore, for that particular xi adversarially chosen, Alice and Bob would still now have to do whatever they were supposed to do without Charlie. You could sort of kick out Charlie by homing on a adversarially chosen I, right? Okay, but before I go there, let me say, why is this model relevant to the problem about data structures? So this would be the last time I would talk about data structure. So the point is, suppose Charlie and Bob, Alice, Bob, and Charlie were asked to compute disjointness. Okay, so now I'm looking at the hard problem, disjointness, the two-party hard problem of set disjointness, which we have discussed many times in this series of talks. So that's a canonical example of a very hard two-party problem, right? Now, can Charlie's advice help Alice and Bob to solve disjointness? Well, the point is, if there was an efficient data structure algorithm for the dynamic shortest path problem, then there is a way for Charlie to give an advice. Okay, that's the connection with data structures. Okay, if there is a good data structure algorithm, then there is a good advice giving Charlie. Okay, so why is that true? So here's what Charlie does. I'm assuming there's a data structure problem. So Charlie is imagining by looking at x1 through xk, this is what happened in phase 1. Because x1 through xk are subsets, right? And so Charlie can build this graph corresponding. So I'm overloading x1. These are n-bit strings, but these are also describing this neighborhood sets. Okay? So Charlie thinks, okay, this corresponds to that particular phase 1 input. Okay? And then Charlie looks at y, and now he knows, oh, this is what happened in phase 2. Okay? And then he also knows that, well, my purported data structure accessed order n tau bits, because that was the time it was given, and updated the graph, updated the data structure, right? That's what the data structure algorithm is supposed to do. And so what Charlie will do is, Charlie knows what are the bits in the data structure that the updation phase went through. And Charlie is going to just send those n tau bits to Alice. Okay? So it's n tau times the addresses of those bits in the data structure. I'm assuming the data structure is not too large, so specifying the address of a particular cell in the data structure is not going to take too much time or too much bits. So it's log of n. So give and take a log, what I'm saying is more or less right, assuming the data structure size is not too large. Okay? Right, so this is what Charlie sends to Alice, right? And now what Alice does is she simulates the phase 3 of the algorithm, data structure algorithm, which we know now queries order tau bits to give out the answer. And how does Alice simulate that? Well, she toggles between Bob and the advice of Alice. Well, first she knows the algorithm perhaps says query bit number 15. Well, first she consults Charlie's advice and sees whether bit number 15 was updated in the second phase. If it is, then she doesn't need Bob. Charlie has given the most current entry in that data structure. If it is not, then she knows, well, it was not updated. So, in phase 1, whatever was there is still the right thing. And so now she consults Bob, who by looking at x1 through xk can tell you what happened in phase 1. Okay? And so just toggling between between Bob and Charlie's advice, she can give out the answer in order tau bits. So all in all, if tau is in polylog of n, then we have established that by just giving very few bits of advice, like order n tau, which is far smaller than k, by our assumption on tau, Charlie has suddenly brought down the hardness of a difficult problem like set disjointness from n to polylog of n. Okay? So that's the connection. And this was first observed by Patrascu, which is why it's a beautiful connection that Patrascu observed. And his conjecture was that, essentially ruling out such a possibility. His conjecture is that if you have a protocol for solving this advice version of the set disjointness problem in which Charlie gives very few bits of advice, little o of k bits of advice, then Alice and Bob need to communicate n to the omega 1. Okay? And if this conjecture is therefore true, then there does not exist any efficient data structure for solving the dynamic shortest path problem. Right? So that's the connection. So, well, this is formally what I wrote down, but yeah. Okay? Any question at this point? So, so this was his conjecture, and having such bounds turns out to be a big deal in data structures because there are no polynomial lower bounds of the form n to the omega 1 known for dynamic data structures. Okay, there are just no lower bounds for any problem. Okay, so here's the next conjecture that Patrascu made in the same paper, which seems very strong, but it's also very tempting. Okay, which is the following. There are two ways he strengthens this conjecture. One is that now he not only talks about the set disjointness problem, but he talks about any problem in general. Okay, so notice that I have an arbitrary f, and if there is if there is a protocol in the advice version where Charlie sends very few bits of advice, so little o of k, that's Charlie's advice. So then, as I said, the intuition is I can kick Charlie out, right? And then Alice and Bob still solve the problem using L of n bits. Then there must be a two-party protocol of cost order L of n, okay, for f. Meaning, whatever post-Charlie communication happens between Alice and Bob can in fact be turned into a genuine two-party problem without Charlie being there. Because Charlie sends so few bits of advice and there are many xi's, right? So this seems like a tempting conjecture. Also, if this conjecture is true, then something very general is going on here. There is one should be able to prove this conjecture without taking into account any special property of set disjointness, right? Because this, if true, is true for an arbitrary function f. Okay, and as I said, the intuition is Charlie's advice gives very little information about many of these xi's. Okay, so Patrascu, when he mentioned this conjecture in the paper, he doesn't talk about this conjecture. Is he talking about a randomized model or a deterministic model? Okay, so we first started thinking about, okay, what happens in the deterministic model? It turns out that in the deterministic model, there's a very simple counterexample to this conjecture, which sounds very simple, but it was the thing that got us going, and I think it's a very illuminating example, which is the following. So imagine, now we are talking about deterministic version. So the canonical hard function for two parties in the deterministic version is this equality problem, right? Where Alice has gotten an n-bit string, Bob has an n-bit string, and they have to find out if they're exactly the same. And you just have to send n bits. It's a simple exercise to prove that. And for every problem we can create this advice version. So let's look at the advice version for the equality problem. So you've got k n-bit strings on Alice's forehead, one n-bit string on Bob's forehead, and then there is an I that they both know, and they have to evaluate whether xi is exactly equal to y. Okay? By themselves, it's a hard problem. So how can Charlie help? So it turns out it's not, it's actually quite simple. So what Charlie does is the following. Charlie looks at all these strings and sees, well, is any string there equal to y? Any string in x1 through xk, in the k list, is it equal to y? Well, if there isn't one, then he just sends a one-bit answer telling Alice, well, you always answer 0, because nothing is equal, right? Okay, so that case is easy. Then the other case is also easy. Suppose there is an xi, which turns out to be exactly equal to y. Okay? So then what Charlie does is just sends so I'm saying here xj that's equal to y. Charlie just sends that index to Alice, which takes log k bits. Okay? And then Charlie disappears. Alice is just acting as a conduit. She forwards that log k bits to Bob. Okay? Bob has got log k bits and the access to x1 through xk. And now Bob learns completely y. Y is worth n bits, but conditioned on this x1 through xk, Bob is able to completely infer y, right? Okay, and so now Bob just outputs the answer, right? So if is xi equal to y is the same as if xi is equal to xj in this case, and xj he knows, so he just gives out the answer. Okay. So yeah, it's just a simple counterexample, right? Charlie gives very short advice, and then in one bit, Alice and Bob can solve the problem. sorry, not 1 bit. Alice had to send Bob the log k bits, so about in log k bits, and k is polynomial in n, so it's order log n. So what is going wrong with the intuition, the simple intuition that one had about the conjecture, is that, well, the intuition was from the point of view of the player who was missing x, right? I mean, it was that Charlie cannot give much information about x to Alice. But this counterexample shows that, well, Charlie would go after Bob, actually. I mean, if he can prepare a very small message with which he can teach Bob about those n bits, then it's much more convenient to do that, right? Alice is just sitting there as a conduit. Okay, and this is what happened in the case of equality. Charlie taught Bob about y if there is anything to learn, meaning if there is a string which is equal, right? If there is no string which is equal, then the function evaluates to a constant on those, and Charlie didn't need to teach anything, right? So the question is, well, maybe the equality function anyways is not a very hard function, because it is true that if you think about the randomized model, equality is a very simple function, right? It's with public coin randomness, it can be solved in order 1 bits. With private coin, it can be solved with order log n bits. So it's probably not a very hard function. Okay, so maybe and anyways, what we need to prove is for the set disjointness problem, which is a much harder problem than equality. So turns out that this this idea about Charlie teaching y is very useful. So for set disjointness as well, one can show the following, that in fact there exists a deterministic protocol in which Charlie will give really very few bits of advice, again about log of n or log square of n, and then Alice and Bob will communicate about square root of n bits. Okay? Sorry, this would be also square root of n. I said wrong. Okay? My bad. Okay, but it will be little o of k, and then Alice and Bob can. So even for set disjointness, the strong form of Patrascu's conjecture is not true, and I want to convince you because it's a very simple idea. It's essentially taking the idea of equality and applying it to the case of set disjointness. So what is now Charlie is going to do? Well, as I said, he's trying to teach, if anything has to be taught, about y to Bob, right? So here, this orange thing is where y is. So and the universe is this whole thing. So initially, Bob has no idea about y. Y could be anywhere in this universe, right? And again, if all the x's on Alice's forehead are disjoint from y, then Charlie has nothing to teach. Just as in the case of equality, Charlie would say answer 0 always, right? or 1, sorry, answer 1 always. So the problem is when there are some x's which are indeed disjoint from y. But each time x is disjoint from y, and if you happen to know x, you learn a great deal about y. In particular, you know that x and y are disjoint, so whatever are the indices, whatever are the elements of x, they are certainly not present in y. Okay, this is exactly the kind of idea that was going on with equality. So now, Charlie would try to spot such an x if one exists, and then try to tell this index to Bob, right, through Alice. Okay, and if x is pretty large, then Alice, by knowing this just log k bits, Bob knowing this log k bits would learn a great deal about y. Okay. So imagine this was xj, and Charlie pointed out this xj. Then the uncertainty in Bob's mind about y sort of shrunk from this whole universe into a smaller segment. Okay, because xj got known to Bob. Okay, so he now knows that y has to lie somewhere here. Okay, this is the idea. So this is a very simple idea, and the protocol also turns out to be actually quite simple. So as I said, Charlie will go after the large sets X, because if X is small, then he will leave it to Alice and Bob, because then the person who sees X can transmit the information about X to the other person, because it's a small set and it will not take too much communication to communicate X. Okay? So, Charlie only picks out the fat X's, the large X's, because if they happen to be disjoint, then his advice, he's getting his bang for the buck, right? So, and specifying this index only takes log k. I'm just repeating myself, and you would learn sigma log n bits. Okay, so as I said, Charlie gives help only for the hard instances. So here's actually the full protocol, and I'll be able to show you, I hope, in one slide. So at the beginning, Charlie is trying to teach Bob, and Bob knows nothing about y. Okay, so the S here will denote the uncertainty of Bob. So this is going to be the subset in which he feels y could lie anywhere. At the beginning, this subset is the whole universe. Okay, and then Charlie tries to find out a particular X that is disjoint from y. Let's say he finds out, and without loss of generality, it's x1. Okay, and he tries to find out a set which is somewhat large. So sigma will be the parameter of largeness. It will something that will plug in later. Okay, so it's going to be a convenient value. So he's trying to find out a set that's larger than sigma, whose size is larger than sigma. Okay, say he finds that out. Well, then he just says, good, I'm going to tell you this index. Okay, and once Bob will come to know of that, then Bob knows that S has shrunk, right, to n minus t1. This is where now y lies somewhere. Okay, then Charlie looks for, now the universe has shrunk from the original S to the new S. Okay, and now Charlie is trying to find large sets with respect to this new universe, because the t1 bits have already been learned. And now Charlie is trying to find out an x2 such that x2 projected down onto this new universe is large. Okay, say he finds that, again, he's going to send the index of that. Okay, and now you shrink the universe further. You keep doing this for, let's say, r rounds. As long as Charlie is able to do that, he keeps doing that. So he's telling you the indices one after the other, and the universe is shrinking. Okay, and he goes on as long as he could go on, and then he finishes. And that's his advice. Okay, so why are we done by this? So the first observation is the following. See, when this, so Charlie's message contains a sequence of indices, right? Indices which he found were still fat. Okay, and this has been transferred to Bob. Now Bob, by just looking at these indices and knowing x1 through xk, is exactly able to calculate this S, the final S, right? Because he has all the information. Okay, and the first observation is he knows that y is completely contained in S. Y has nothing outside of S. Okay, because that's the thing, that's the way we went. And the other thing is, what he knows is now he looks at this set of x1 through xk, and he projects them down to S. He can calculate this S. And if he sees that, after projecting, a particular set is still very large, larger than sigma, he knows that that set must be intersecting with y. Because if it did not intersect, then Charlie would not have stopped. Because the assumption is Charlie goes on as long as he could. Right? So, after, when you project it down, and if you see the set is still very large, then you know already the answer. The answer is, well, it must be intersecting with y. Okay? So that's the only way you could be large. Or you are small. Okay? And then you don't know the answer. Maybe it will intersect, maybe it will not intersect. Okay? So by easy here, I mean that it's small. Okay? So let's now try to estimate, how many bits did Charlie send? Well, Charlie sent, if it went on for r rounds, Charlie sent r times log k bits. Okay? Because each disclosing each index took log k bits, so he sent r log k bits. But each time he sends, in each round, he's shrinking the universe size by sigma, and so his number of rounds is at most n over sigma. Right? That's a simple thing. So the total number of messages that he sends is n over, the total length of his advice is n over sigma times log of k. Right? And now here's the protocol. Okay? So the protocol is now very simple. Bob, on receiving this amount of information, Bob is able to, as I said, Bob knows, he looks at xi, projects it down to s. If he sees it's larger than sigma, he gives out the answer himself that they are not that they intersect, that they are not disjoint. And if he finds that it is less than sigma, then he doesn't know. So he transmits this to Alice. Okay, he transmits the projection of xi onto s, only that part. Okay, because the intersection is contained completely within s. And so transmitting that by assumption therefore takes sigma log n bits, right, because it's smaller than sigma. Okay, so now if we set sigma to square root of n, that gives you the optimal bound, which now therefore says that Charlie has sent square root of n times log k bits, and Alice and Bob, post this advice, have communicated square root, at most square root of n log n. Right, that's the protocol. Okay, so it's a completely deterministic protocol, and again, the whole idea is sort of you can teach Bob about y communicating very few bits. Okay, so even a hard function like set disjointness, which was hard for the randomized two-party problem, under this advice model can reduce the cost at least quadratically. Okay, so the point is, if one could show that you can never save for a hard function more than polynomially many bits, then we would still be fine, right? We do not need to prove the strongest form of Patrascu's conjecture, because an n to the omega 1 lower bound is already good enough. Okay, it would be fantastic to have that. So if there's a way to show, for example, that no matter what you do, you can't save more than polynomial number of bits for a hard function, you would be fine. Okay, so at this point, this possibility is still open. Unfortunately, what we were able to show, again, this taking this idea sort of one level above by using ideas from learning theory. So the whole point is now, Charlie is trying to teach Bob about y, right? And so we take recourse to formal notions from computational learning theory, and then we are able to show that there exists a function f that has sort of randomized two-party complexity as high as possible, like set disjointness omega n, but the advice version of this problem has efficient, super efficient deterministic protocols, okay, in which Charlie sends order log square n bits of advice, and then Alice and Bob only need to communicate order log square n bits. Okay, so how much time do I have? Okay, so just to give you an idea about this result, I probably wouldn't be able to sort of tell you the whole thing, although it's once you have the right ideas, it just takes a slide to prove this result. But let me try to convince you how learning theory at least comes in, a little bit more detail about it. So in computational learning theory, what happens is there's a teacher and there's a learner, and the teacher holds a concept class. I mean, there's a concept class, a set of functions that and teacher holds a particular function called the target function from this set of functions, and the learner is trying to learn the function that the teacher holds. The learner knows about the concept class, and the setting is the following. The teacher is going to teach by example, so there's some distribution unknown to the learner, okay? And when the learner is trying to learn a function, basically the learner asks for examples from the teacher, okay? So each time the learner asks for an example, the teacher provides samples a point at random according to this unknown distribution mu, and provides the example and the evaluation of the function on that example to the learner. Okay, and this goes on. Maybe the learner says, well, no, I didn't yet learn it. Give me another example. Again, the teacher gives an independent sample according to the same distribution mu, okay, a point, and then gives the valuation of the function on that point. Okay, this goes on for a while, and at the end of it, after seeing some time, maybe the learner declares, well, now I've got the function. I think I know what the function is. Okay, what does it mean to know the function? Here's the test that the teacher is going to do. The teacher is going to again sample a point from the domain independently according to the same distribution mu. Okay, and the learner should be able to give back the answer with high probability on that point. Okay, that's the only test. Okay, so the function that the learner may have thought he has got could be actually different from f, but at that sample point with high probability it should be right? So this is called the PAC model, it's over there. The point is you want to approximate the function f well with high probability. So it's probabilistically approximate learning. Okay, so this is a standard learning setup introduced by Valiant called the PAC learning model. There's lots of work that has been done on that. Okay, so and the key question here is how many examples are needed by the learner to learn a particular concept class. Okay, now what has that got to do with communication? So here's a very natural connection to communication. So notice that we have a communication matrix. When you have a two-party problem where the rows are indexed by the inputs of the x player and the columns are indexed by the inputs of the y player, and now each column you can think of it as a function on the x variables, right? Okay, so each column with each column of this matrix you can associate the induced function on y, right? So I can therefore identify each column with a function, and this forms a concept class, right? So a matrix here is just exactly a concept class because each column is a concept, right? And so I can ask questions like, given a matrix, which we deal with in communication matrix, what's the learning complexity of this matrix? Okay, just as we have thought about communication complexity, there's another combinatorial question, which is what's the learning complexity of this matrix? Okay, and here's a beautiful theorem due to Cherstov, who showed the following: that there are functions with linear randomized two-party complexity. So the matrix there is very hard from the point of view of communication complexity. Okay, they have linear randomized two-party complexity as high as it could be. But the concept class induced by that matrix can be learned by by a constant number of examples. Okay? So the separation between the learning complexity and the randomized complexity is as high as it can get. Okay?
What's the connection to the Kramer-Brown result where we also have one-way communication?
So that is one-way communication under product distribution. Okay, yeah, and that's the connection that he uses as well. Okay, so what we observe is the following thing. So our result is the following, and I find it a sort of an intriguing connection, which is that, well, now in our model, if I look at the advice model. Then if this concept class C of f, okay, can be learned from m examples, meaning, and assume m is sort of very small, then in fact the advice problem has a randomized protocol of total cost order m log k. Okay, so for example, if m is constant, the total cost would be order log k, right? But if you combine this result with the theorem of Cherstov, then it already shows that there is a function whose two-party complexity is very high, as high as it can be, like set disjointness. However, in the advice model, its complexity drops down to order log k, right? So, and that completely kills the strong form of Patrascu's conjecture. Okay, so the sort of essence of this is you cannot sort of have an information theoretic argument which sort of works in a black box fashion. You have to dig into the function and use somehow the specifics of the function to argue that it remains hard in the advice model. So I think I have 5 minutes. So let me spare you this slide, which was basically a proof of that. Actually, it's not hard, but yeah. So you can build a protocol, and I want to just sum up in the following way. So disproving Patrascu's strong form of the conjecture, in every of our protocol, there are like 2 features which are very, very special. I mean, it seems like we have not explored the entire domain of all possible protocols, right? Our protocols all have a very restricted feature, which is the following. Well, Charlie in the original setup is allowed to send little o of k bits of advice, right? And k, if you remember, is n to the 1 plus gamma, right? So little o of k, for instance, does include things like n times polylog of n, okay, which is super linear, but still smaller than n to the 1 plus gamma for any constant gamma, right? So k is n to the 1 plus gamma, and little o of, I mean, certainly n times polylog of n is in little o of n, right? And so, oh, sorry, yeah. Right. So certainly Charlie is allowed to send that many bits of advice, okay? Whereas the advice that we have sent, we have used is really small. So the longest advice was given for the case of set disjointness, where the advice length was square root of n, okay? So it seems like with more advice from square root of n up to n times polylog of n, you can perhaps do much more interesting things. Okay, so it's a very interesting question from the point of view of understanding this. Or can you? I mean, can you sort of compress Charlie's advice always and make it small? Okay, we don't know. I don't know of any interesting protocol where you really need the budget that has been provided to you. Okay, so that's an intriguing question. So all our protocols, they have very short advice. And then the other feature that's sort of very special is post Charlie's advice, you allow Alice and Bob to communicate with each other as if they were in the full unrestricted 2-party problem. So potentially there could be arbitrary interaction. Okay, and however, all our protocols, if you think about it, they are like very simple interaction. Alice, the recipient of Charlie's advice, was just transferring the advice to Bob, and then just Bob was giving out the answer. Okay, or Bob was sending just one message, and Alice was giving out the answer. So there's very limited Alice-Bob interaction. Okay, so this is a bit of a mouthful. We call it sort of 1.5 round because, not only there's very limited interaction, Alice sort of does not use her knowledge of I in giving this. So it's a technical thing, but the point is the Charlie's advice is short, and post Charlie's advice, the interaction between Alice and Bob is very limited and very restricted. Okay, and what we could show is that if you do have such restrictions on protocol, then you can't do anything better. For set disjointness, you can show under these restricted protocols, you can have you need square root of n bits of communication post Charlie and Bob, post Charlie's advice. Okay. In fact, if you have, what we can show is something stronger. If you have any one of these features, that's going to kill you. Okay, so too short advice is bad, and too limited interaction is bad. Okay, and so what I find is an interesting conjecture is, so how does this number square root of n pop up? So what might be a way to resurrect this Patrascu's conjecture, I haven't thought about it in a great deal, is that you say that the actual complexity, advice complexity, is not the original randomized complexity, but the complexity under product distributions of Alice and Bob. Okay, and if you recall, under product distribution, set disjointness has exactly square root of n complexity, and the other counterexample will also fail. Okay, I'll stop there. Thanks.